This is the first of several videos about enthalpy. We're going to be talking about the definition of internal energy, the definition of enthalpy, what state functions are, and how these relate to Hess's law. So we'll start with internal energy. In the last video, we talked about calorimeters, about measuring the transfer of disordered energy as heat. And here we're going to return to that idea of energy transfer. Energy is transferred between objects in a disordered or ordered way as heat or work. And so we're going to name the total energy that an object has after those energy transfers have happened. The total energy an object has after the transfer, that is called internal energy. And we usually represent that as U, but some textbooks use E for energy, so watch out for that. Internal energy. And so now we don't actually have a thermometer we can stick into an object and measure its internal energy. That's not something we're able to do. We can't actually measure U. But what we can do is measure how it changes in the form of energy transfer. So the change is going to be deltaU, and that is something we can measure. So we said there were two ways for internal energy to change. It can be through heat or through work, like we talked about at the beginning. So deltaU is going to be Q plus W. Disordered transfer plus the ordered transfer. And I want to be very specific about the kind of work we're talking about here, because we talk about work a lot in physics as well. So this type of work is specifically pressure volume work. And this is the type of work that's done by gases. Expansions or compressions are pressure volume work. So the formula that we're going to use for work is negative pressure times the change in volume. This is the pressure volume work that we're talking about. And you'll notice that the units here are going to be a little bit weird. Pressure is usually measured in units of atmosphere, and volume is usually measured in liters. And somehow we have to get joules for work, because we need to have joules for heat and joules plus work to equal joules of internal energy. So atmosphere liter is actually a unit for measuring energy. It's just kind of a weird one. The conversion factor is 1 atmosphere liter equals 101.325 joules. So that's a conversion unit that you might need to use in some of your homework problems. So here we've talked about Q in the last video, about how a positive value for Q is called endothermic. And that is when heat is going into the system. So let's give a similar definition for work. So if work is positive and it's going into the system, that's called compression. That is when the surroundings are compressing, are doing work on the inside and compressing it to a smaller volume. Work is going into the system. We defined a negative heat value as exothermic when heat was leaving the system. So for work, when work is leaving the system, we call that expansion, meaning that the system on the inside is doing work on the surroundings as it pushes and makes that a larger container. So it's expanding the container, doing work on the outside, negative work. Okay, so we've talked about internal energy is heat plus work, but this is a chapter on thermochemistry. So what we really care about in this chapter is heat. And so we have a special name for just this portion of the internal energy, and that name is the enthalpy. And because we're starting to run out of letters, we're going to use H, because there's an H in the word enthalpy. So enthalpy is the variable which we use to measure heat flow under a certain condition, the one that we most commonly experience. Heat flow at constant pressure. And remember, in the last chapter, we used Q to represent heat flow. So if this is heat at constant pressure, we'll call it Q sub P. So enthalpy is Q sub P, heat flow at constant pressure. So the enthalpy and the internal energy are related by this formula. Delta H enthalpy is equal to delta U, the internal energy, plus P delta V. And that is a formula you are going to be using. So I've made up an arbitrary mnemonic device off the top of my head to help you remember that about hedgehogs. So the device is hedgehogs understand your point of view. Delta H equals delta U plus P delta V. That may or may not be helpful, or it may be completely random, but there you are. So delta H equals delta U plus P delta V. And so let's see if we can do some substitutions based on the formulas that we know for delta U already and for the formula that we know for W, because W is related to P delta V, and we can simplify this formula to show that enthalpy change is equal to change in heat at constant pressure. So let's substitute for W and for Q. For U, sorry, W and delta U. So we can substitute for delta U. So delta U equals Q plus W plus, and then P delta V is the opposite of work. So we'll substitute in a negative work. And then if we simplify that, the W and the minus W cancel, and we end up with delta H equals Q. But remember, not just any Q, Q at constant pressure. Okay, and so now that we have delta H as one of the variables we're comfortable using, let's go and add it into our table of positive and negative interpretations. It's going to be the same as Q. So if this delta H is greater than 0, it's going to be an endothermic reaction. At constant pressure, there will be heat going into the system. And when delta H is less than 0, it's going to be an exothermic situation. At constant pressure, heat will be going out. I hope you enjoy arbitrary mnemonic devices, because there will be more of this chapter. Okay, so we've talked about this, and this is the enthalpy value, but sometimes these are difficult to measure and we want to do calculations with them, so we need to look them up in a table of values. So in a table of values, we can look up what's called a standard enthalpy. So the standard enthalpy is delta H with a little circle at the top for standard. And the conditions for the standard value are a pressure of 1 atmosphere, concentration of 1 molarity, and technically, unless otherwise specified, a temperature of 0 degrees Celsius. The temperature is not technically part of this definition of standard conditions. However, because it's part of STP, most tables are listed with this value anyway. So we'll put an asterisk here. These values come from reference tables. Our favorite thing, we don't have to measure it ourselves. And so you'll find a table at the end of your book, and then when you're doing sapling homework, you will find a table embedded in the sapling homework with the reference values that you need. So these values, like delta H, are a particular type of variable, and that type of variable is called state functions. So we're going to spend just a hot second talking about that and what that is. So state functions are special kinds of variables, and their property is that the value of that function only depends on the current state of the system and not how it got there. Depends on the current state, not how it got there. So if you've heard the motivational phrase about how it's not about the destination, it's about the journey. Well, in the case of a state function, it literally is only about the destination. It is not whatsoever about the journey. And I'll show you why. If I'm trying to travel from point A to point B, I can make my journey go wherever I want between those 2 points. I can take a line, the shortest distance between 2 points. I can take a detour and swing by the DQ, the Dairy Queen, on my way to point B. Or I can head off in a straight line and then turn around because I forgot my wallet and then head back to point B. And no matter which route I took to get there, if I take my final position minus my initial position, I'm going to get the same value. Because this distance in the picture, this change of location, is a state function. So it's the same for all paths. So let's see if we can identify other variables that would be state functions. So over Christmas, my plan is to fly to California, where I got my PhD, and visit my friends. So if I was taking this trip, which of the following items would be state functions of the trip? Meaning that no matter when I did the flight, if it was on December 1st or December 4th or on December 25th, this value would always be the same. So elevation change. Let's see, California has a particularly low elevation, and Wisconsin also has a particularly low elevation. And no matter what day that I decided to fly there, the elevation of Wisconsin and California would always be the same. However, for the miles traveled, that may differ from day to day. The plane might have wind that might be blown slightly off course. We might have to shift slightly north or slightly south to avoid another plane coming. So this one is not going to be a state function. It could be different on a different day. The time zone change. California is in Pacific time, which is 2 hours earlier than Wisconsin. No matter when I go and visit, that is always going to be true. So that one, time zone change, is a state function. But time spent traveling might depend on when I traveled. If I got to the airport really early, the amount of minutes that I spent in the airport would be longer on that particular trip than if I decided to make the trip and show up 30 minutes before the flight left. So this value could change depending on how I made my trip. So that one's not a state function. And then, of course, the number of snacks that I eat on the trip definitely depends on what I had for breakfast that morning. So that is not a constant with my journey, and that is not a state function. So these two, elevation change and time zone, those only depend on the destinations. The destination is the same for both of these, but for miles traveled, the amount of time I spent at the airport and the number of snacks eaten, those depend on the journey. And if it depends on the journey, it's not a state function. And the reason that we are talking about this in such great detail, with such fabulous examples, is because the enthalpy and the internal energy are state functions. And we can use these properties to our favor. And we are going to talk about how to use the state function property in the next video.